Okay, as promised, I'm going to go over the answers to some of the practice problems that were on the study guide. So just to remind everyone that the exam is just going to cover up to section 3.2, so that's an important change. All right. So if you recall, I said there'd be two types of questions, basic knowledge questions and some problem-solving questions. So let's go over the basic knowledge questions first. Okay, so what causes electrons to stay near the nucleus of an atom? We're talking about electrons and the nucleus. And so with these basic knowledge questions, we're thinking about sort of the big major concepts in terms of the chapters and the material that we've covered. So what do we know about electrons? Okay, well, we know that electrons are negatively charged. And what do we know about the nucleus? Well, we know that the nucleus contains both protons and neutrons. One of the important concepts for this exam is to have an understanding of the basic structure of an atom. And so the protons and the neutrons are in the nucleus. The neutrons are neutral, they have no charge. Okay. And the protons are positively charged. So one of the things that we talked about that holds electrons in an atom is the fact that there is attraction between the unlike charges, or the charges of opposite signs, the positively charged protons in the nucleus and the negatively charged electrons. So what causes electrons to stay near the nucleus of the atom? It's the attraction between negatively charged electrons and the positively charged protons in the nucleus. All right, so that's that question. Okay, so now let's look at the nucleus itself and think about the forces that stabilize the nucleus. Okay, so another big important concept, okay, is nuclear stability, the forces that stabilize it, right? Nuclear stability. Okay. All right, so we've got protons and neutrons in the nucleus. And when we talked about the forces at play in the within the nucleus, what we talked about was the strong nuclear force. So the strong nuclear force is that very short-range force that holds together the protons and the neutrons in the nucleus. Okay, so that holds the protons and the neutrons together in the nucleus. Okay, so keeping on with the theme of it's important to understand the structure of the atom, where is most of the mass of the atom? Is it in the nucleus, the electron cloud, or is it both? So if we think about, if we go back to our subatomic particles, okay, so let's go back to those and we'll add more features about what we know. The electrons are negatively charged, and remember that we say they have zero mass, or we neglect any mass they have. Okay, and both the protons and the neutrons have one atomic mass unit each. Okay, so if the things that have mass are the two particles that are found within the nucleus, okay, then most of the mass is in the nucleus. where the protons and the neutrons are. Okay. All right, so the next question is, when chemical reactions occur, what changes? The shape of the nucleus or the shape of the electrons? Now, we haven't really talked about the shape of electrons or the nucleus very much at all. But one thing that we did mention is that chemical reactions, okay, are going to be rearrangements of electrons. We made the point that the nucleus is not going to change in a chemical reaction at all. It's what the electrons are doing, okay? So in this case, we can kind of deduce from what we've said in class, okay? So nucleus doesn't change in a chemical reaction. Thus, the shape of the electrons must be what changes, okay? All right, so we've got some more basic knowledge questions, okay? So we introduced a whole bunch of terms when describing elements and atoms, and we use two terms, isotopes and allotropes. So we'll answer this question by defining the two terms, okay? So isotopes, remember, are atoms of the same element with different numbers of neutrons in the nucleus. Oops. Oh, I'm making a mess here. There we go. Neutrons in the nucleus. Okay, now an allotrope, okay, is something entirely different. Okay, so allotropes are atoms of the same element existing in different physical forms. Okay? And there are only a few elements that can form allotropes. So, two examples that we looked at were carbon. So one example is carbon that can exist as either graphite or diamond. Okay, it also can exist as what we call buckyballs. So that's another arrangement, carbon nanotubes. Right? And then the other example one of the other examples that we used was oxygen. So oxygen, remember, can be O2, like the gas that we breathe, or it can exist as O3, so where you have three oxygen atoms connected, and that, if you recall, is ozone. And that's a protective gas in the atmosphere, but you wouldn't be able to use it if you breathed it in. Okay, it's not one that can be used by our body to process our metabolism like oxygen gas can. Okay, so the basic knowledge question number 6 here, this is from section 3.3. So it's not going to be on the exam, okay? So that material is not going to be on the exam, okay? But we'll give you a preview, and we'll tell you that n is what we call the principal quantum number, and as n increases, you get farther away from the nucleus. So if this is our nucleus that has protons and neutrons in it, okay, n equals 1 would be the lowest energy level, and those would be electrons closest to the nucleus. And then the next one would be N equals 2. And that's farther away from the nucleus, higher energy region, and so on. Okay. All right. Same thing with question number 7. It's also from section 3.3, and therefore not on the exam. Okay. And we'll be talking about the absorption and emission of energy and what happens to the electron energy levels and their principal quantum number after the days of class after the exam. All right, so let's talk or just go over the problem-solving questions, those examples. Okay. So there were a couple type of questions that you can kind of expect to see. Ones where you're using relationships, the mathematical relationships that we've talked about, things like density, the energy of a photon, the relationship between wavelength and frequency, okay? And then there will be things like unit conversions, and then sometimes you're going to have to take more than one step to an answer, okay? So just like there are some places you can travel going on only one road, but there are other places where you have to go on several roads to get there. Okay, so we're going to look at a couple of those types of examples. Okay, so a metal has a mass of 28.6 grams and a volume of 7.53 centimeters. What is its density? So we have a relationship between density, mass, and volume, and that's density is the mass divided by the volume. Okay. So you're given one version of each of the relevant equations on the reference sheet. You might need to rearrange the equation for the quantity that you want to solve for. But in this case, all right, we've got the mass and the volume. So there's our mass, there's our volume, so we don't need to do any rearranging. And we're just going to be taking 28.6 grams, dividing it by 7.53 centimeters cubed. Both our numbers have the same number of significant digits. This number comes out to be 3.798 grams per centimeter cubed when I put it into my calculator. But I only have 3 significant digits, so I'm going to round that to 3.80 grams per centimeter cubed. Okay, so this is 3 significant figures, just like our original measurements have 3 significant figures. Okay, so the next question is also using density. Okay, but what we want to know is how many atoms are in a piece of lead. Okay, and you're given the density and the volume. Okay, and so in this case, we don't have any relationship that's going to directly relate our density to number of atoms or volume to number of atoms, right? The one thing that we can relate to number of atoms is the unit of the mole. Okay, so that's the thing that somehow we have to get to. Okay, so we can go from moles to number of atoms. We know that. So we're kind of work backwards here and figure out what we need to do with the information that we're given. Okay? All right. And so how do we figure out the number of moles we have? Well, we can use the masses from the periodic table. Okay? So to get to moles, okay, whoops. All right. So to get to moles, we can go from mass in grams to moles by using the mass of that element from the periodic table. Okay. All right, and then, so how are we going to get the mass? Well, we are given a density and we're given a volume, right? So we can get the mass, okay, from the density and the volume. So we're going to use the density and volume to determine the mass. So this is exactly the type of sort of multiple step question that you may have one of on the exam, okay? So there will be one multiple step question at least on the exam. All right, so first, okay, let's solve our density equation for mass, okay? So the way we can rearrange this equation for the mass is we can multiply both sides of the equation by the volume. So density times volume is going to equal, all right, if we multiply both sides by the volume, I'm just going to show you that, again, the volume cancels out, okay? So mass is going to be equal to the density times the volume. So our mass is equal to 11.33 grams per centimeter cubed times 6.32 centimeters cubed. And that comes out to be 71.6056 grams. Now, I'm going to keep, all my digits until my final step, and then I'm going to worry about significant figures, okay? Okay, so now we have the mass, okay? So we're going to find the number of moles, okay? So we've got that, and so now we're going to convert to moles. That's going to be the next step of our calculation, okay? And how we do that, again, is we need to know how many grams there are in 1 mole of lead, okay? So I want to wind up in the units of moles, right? And so I'm going to look for what is the mass of 1 mole of lead on the periodic table. So if we go here, lead's symbol is Pb. So if we can find Pb on the periodic table, it's over here, element number 82, and its mass is 207.2. And when we're talking about a mole of those atoms, it's 207.2 grams in 1 mole. Okay, so when I take 71.6 and I divide it by 207.2, I get 0.345587 moles. Okay. All right, so now I know my number of moles, and so I'm going to use Avogadro's number to go from moles to number of atoms. Okay, so from moles to number of atoms, anytime we want, a number of particles, we're going to be using that Avogadro's number. So I've got my 0.345587 moles, and I'm going to multiply it by Avogadro's number, which is 6.022 times 10 to the 23rd, and that's going to be atoms in 1 mole. Okay. All right, so my final answer winds up being 2.08 times 10 to the 23rd atoms. And what you'll notice is at this point, I wound up rounding to the correct number of significant figures because my volume measurement had 3 significant figures in it. So here I have 3 significant figures. Okay. All right, so that was kind of a long one. And most of the problems on the exam are going to be short. But again, there will be at least one that will take you, a couple steps to do. Okay. Okay. So here's one. What's the mass of a sample of chromium, okay, that has the same number of atoms as a 23.6 sample of boron? So the key concept here, okay, that you need to know is that same number of atoms you can interpret that as same number of moles. Oops. Because moles is our unit that we use for counting atoms, okay? All right, so if we figure out how many moles, okay, there are in 23.6 grams of boron, so 23.6 grams of boron, okay, and the atomic symbol for boron is B, okay, and its molar mass is 10.81 grams per mole. So this is 10.81 grams per mole of boron, okay? And so we want to know how many moles we have, okay? So we're going to convert that from grams into moles. So here we want the grams to cancel, so we're going to put it down on the bottom. We always keep its number with it, okay? And we have the 1 mole. Okay, so this is grams of boron and 1 mole of boron. So in this case, okay, I've got, the number comes out to be 2.18 moles of boron, okay? All right, so that tells me, right, I want to know how, same number of atoms, okay, so that tells me that I have 2.18 moles of chromium, okay? And if we look up chromium on the periodic table, here it is, symbol is Cr, and its mass is 51.9961. So this is chromium, and its molar mass is 59 point, what did I say, 9961 grams in 1 mole, okay, of chromium. So I'm just going to do for chromium the reverse of what I did for boron. For boron, I wanted to go from grams to moles, and for chromium, I'm going to want to go from moles to grams, okay? So I'm going to multiply it by the molar mass as the conversion factor. And in this case, I want to keep the grams on the top because that's what I want my final answer to be in, that unit. And here's my mole. All right, and that number comes out to be, let's see, 2.18 moles of chromium. It comes out to be 113 grams, okay? And again, my number is in the correct number of significant figures because my original mass had 3 significant figures, okay? So that would be my answer to that one. All right, so the last problem-solving question is one like we've done in class where we're taking a frequency or a wavelength and we're trying to figure out, what the corresponding wavelength or frequency is, and then we're trying to relate that to the amount of energy that that light is carrying. Okay, so first we want to know frequency, and we're given the wavelength. So our relationship between frequency and wavelength is that our frequency, remember that's nu, and our wavelength is lambda, okay? And we need to, so our frequency, okay, times the wavelength gives us the speed of light, okay? So that's our relationship, right? So, but what we want to know is what the frequency is, and we're given the wavelength. So we want to solve this for the frequency, because that's the thing we want to know. And so frequency is equal to the speed of light divided by the wavelength. Okay. All right. So the speed of light is our constant, right? So here's our constant, 3.0 times 10 to the 8th meters per second. And we're going to divide that by our wavelength, 462. Remember, nanometers is 10 to the minus 9th meters. Okay, so times 10 to the minus ninth meters. And frequencies are always in units of seconds to the minus 1. And this comes out to be 6.49 times 10 to the 14th meters. Okay. Oh, wait a minute. Not meters. Sorry, I had the wrong unit. Seconds to the minus 1. Okay. All right. Okay, so the last thing we're going to do is we're going to relate that to energy. And remember, for energy, we're just going to multiply it by a constant. Okay, so the energy of our photon is our frequency multiplied by Planck's constant right here, which is 6.626 times 10 to the minus 34 joules per second. So my energy is equal to h nu. Energy is equal to 6.626 times 10 to the minus 34 joule per second. And we're going to multiply that by our frequency, which is 6.49 times 10 to the 14th second to the minus 1. Okay, so those seconds are going to cancel out, leaving me with my energy in joules. And in this case, I get 4.30 times 10 to the minus 19 joules. Okay, and that is the energy of a photon of 462 nanometer light. Okay, so that was it for all of the sample problems that we had. So hopefully you'll get the feel for the types of questions that are going to be on the exam, and also you get somewhat of an idea of how to solve a multi-step problem from the one we did here. All right, see you on Monday.